Okay, today's lesson is to learn the difference between mass and weight. Now, the difference between mass and weight is something that confuses a lot of people. A lot of people think they're the same thing, but they're actually very different things. And so today, you should be able to understand why, like what the difference between them is and why we have differences between them. All right, so first I'm going to talk about mass, and I'm going to understand like what is the definition of mass. All right, so the definition of mass is this. Here's a chemistry definition of mass, right? The chemistry definition of mass is the amount of matter in objects. So say you have these two different objects right here, okay? So one clearly has more mass than the other. Now, from a chemistry point of view, why would this one have more mass than this one? Well, it's just because if you literally count the number of atoms that this is made up of, right? 1, 2, 3, 4, 5, 6, up to the trillions and billions of atoms that are in this thing, you would have more atoms in this thing than you have in this thing. So that's why this has more mass than this guy, okay? But that's kind of, like I said, more of a chemistry idea of mass. And so from a physics point of view, what's the significance of one having more mass than the other? And I guess one thing that you would do sort of is that like, all right, if you had these two, how could you even just judge which one has more mass? Well, I guess you could look at them and see the size. But the problem is that that wouldn't account for density, right? So if you had your eyes closed and they were the same size and one had more mass than the other, how could you tell that one had more mass? And usually what most people do is just do something like this. They sort of shake them around a little bit and sort of feel, and then one would just feel like more massive than the other. And really, that's a good intuitive way to actually sort of get a sense that one is more massive than the other. But let's understand actually what very specifically is happening there that allows you to say this guy has more mass than this guy. So when you shake them around like that, what you're actually doing is providing forces onto these guys, like creating forces onto them to cause them to accelerate. And then what you'll notice that some of them are more sluggish than others. They don't accelerate as readily. Like I tried to accelerate this thing's kind of hard to accelerate, and this thing, wow, accelerates really easily. And so that from a physics point of view is actually the difference between two objects with mass, all right? So from a physics point of view, the object with more mass is then the one that actually is the one that has a slower acceleration if you apply the same amount of force, right? So larger masses have slower accelerations. So from a physics point of view, this is the significance of mass, right? Yes, it has more matter, but from a physics point of view, what is the significance of having more matter? Well, if you apply a force, all objects should accelerate, but larger masses will accelerate less if you apply the same amount of force. Or another way you could look at it is you need more force to give it the same acceleration, okay? Now, a common misconception is that massive objects are just slow. Massive objects are not slow. They're just hard to accelerate, okay? So low acceleration, yes, does mean harder to speed up, for sure. So an obvious example is like an ocean liner. An ocean liner is really hard to accelerate. So acceleration takes a really long time, and it takes a long time for that thing to speed up. However, a common misconception is that massive objects are thus slow. They are not slow. They just accelerate slowly. And remember, there's a difference between acceleration and velocity. Because if you have a slow acceleration, if it accelerates for long enough, it'll eventually be going pretty fast, all right? So that's actually, let me go back to the example of the ocean liner. They actually eventually, I mean, once they speed up, it may take them like a couple days to get up to speed. But once they get up to speed, they actually are going pretty fast, all right? So an ocean liner, like one of those big tankers in the middle of the Pacific Ocean is actually going really quite fast, all right? It just took days to get up to speed because it accelerates so slow. So they can go pretty fast. All right. Now remember, acceleration is not just speeding up. Remember, acceleration can also mean slowing down. And the same thing holds true right here. Larger masses have slow accelerations. That also means, all right, that they are also harder to slow down once they get up to speed. All right. So like going back to that ocean tanker again, right? Okay, it takes 2 days or so. I may just make that time up, Bart. Let's just say it's a long time. It may take a very long time for it to get to speed. But once it gets up to speed, it could actually be going really fast. So it's cruising super fast. But then when it comes time to slow down, it takes forever for that thing to slow down too, because the large mass makes it hard to accelerate. And when I say accelerate, I can also mean decelerate. Okay, so slow acceleration can mean hard to slow down. So then when it's time for that tanker to go into port, maybe like, oh man, we're like 10 miles away from port. We should start slowing down now, right? Whereas a less massive boat can slow down a lot quicker, right? So remember, acceleration does not necessarily mean speeding up. It could also mean slowing down, all right? So a small acceleration might mean slow to speed up, also like hard to slow down. And remember also, acceleration can mean turning too. So it's hard to change direction. So basically massive objects just don't like to change their velocity, right? Whatever they're doing, they want to keep doing it, right? Whether it's going fast or going slow or stopped or something like that, they want to keep doing that. And it's hard to change its velocity, all right? So yeah, that is large mass. One good way then you could think of what mass means from a physics point of view is that more mass means more inertia. Remember, inertia is defined as the tendency for an object to stay at a constant velocity, all right? So objects with more mass, from a physics point of view, the significance of that is that that object does not want to change its velocity. It really likes to keep its constant velocity. So like I said, very difficult to speed up, very difficult to slow down, very difficult to turn, okay? So that's what I said you were doing right here, right? This object, the fact it's more massive, is very difficult to speed up and slow down, right? And turn and stuff like that. This object is much easier to speed up and slow down and turn, okay? So now it's time to talk about weight. What is weight? Weight is something very specific. It is the force of gravity. So that those FBDs you've been doing, that downward arrow you've been drawing, that you label FG, that is also called weight. So you can call that the force of gravity and you can call it weight. So weight and force of gravity are literally the exact same thing. They're synonyms for each other, okay? So when you say weight, you also mean force of gravity, okay? Now, I'm gonna show you then how to calculate weight and thus talk about why people sometimes get weight and mass mixed up. So here is how you calculate weight on the planet Earth. So weight, which is the same as force of gravity, of course, right, is equal to the mass times this other number. So I'll explain what the other number is later, all right? So to find the weight, you'll take the mass and you multiply it by 9.8. And that number right there, that number 9.8, is a number that is specific to being on the surface of the Earth. Okay? So if you're ever not on the surface of the Earth or on another planet, then this number will be different. And that is one way you can change your weight. Right? One way you can change your weight, yes, is to have more mass. And I think that's where some people kind of, yes. So if you change your mass, you will have more weight. But you can also change your weight by changing this number by going to a different planet. All right? I'm going to explain these units a little bit later. All right? But the idea is that weight, aka the force of gravity, depends on mass, but it also depends on this number, which is dependent on what planet you're on. Okay? So let me talk about these units right now. Mass is a unit that is measured in kilograms. In chemistry, you oftentimes use grams. You can also have milligrams. In physics, our standard unit to use is kilograms. All right. And if you use kilograms, this number 9.8, this force will be measured in unit called newtons. All right. So forces are always measured in units of newtons, abbreviated with capital N. All right. So now you can see this. What is the units of weight? Well, how about this? The unit of mass is kilograms. The unit of weight is not kilograms, because the weight is a force. And I just told you right now, all forces have units of newtons. So the units of weight is going to be newtons. So to say that you weigh a certain number of kilograms is kind of a mistake. You're using your units wrong. If you want to report a weight, you would report that in newtons. All right, so let me give you an example of a numeric example. So let's see. Say you had an object with a mass of 10 kilograms. So the appropriate thing to say, that object has a mass of 10 kilograms. Now, if you want to report the weight, the way you find weight is you calculate the force of gravity, which is to take that mass and multiply it by this number 9.8, and this guy's weight is 98 newtons, right? So this object has a mass of 10 kilograms and has a weight of 98 newtons, okay? That's actually how you calculate these two things, okay? So let me then sort of talk about different planets then, that number 9.8, right, that I said was specific to the surface of the Earth, right? Here would be a table of what it's like on different planets, what that second number is going to be. So you see this number 9.8, that is specific to being on the surface of the Earth. If you're on the surface of any other planet, that second number is going to be different. So what does this mean about the difference between mass and weight? So say you're an object with mass of 20 kilograms. So this object right here has a mass of 20 kilograms, okay? No matter what planet you're on, that object has the exact same mass. And it kind of becomes easy to understand because the mass is defined as the number of atoms in this thing. And just because you move this mass to a different planet doesn't change how many atoms are in this object. This object has 20 kilograms worth of atoms in it, right? So no matter what planet you're on, it's going to have the same mass. However, if you take it to different planets, it may have different weights. Why? Because that second number is different. Sorry, I'm blocking it, right? So the weight on Earth would be 20 times 9.8, 196 newtons. But then the weight on Mercury would be 20 times 3.6, and the weight on Jupiter would be 20 times 25.9, right? So the mass is the same no matter what planet you're on. The weight is different depending on the planet's gravitational field, okay? So what significance does this have in a practical manner? Like then what is the difference between mass and weight from beyond just like calculating numbers, all right? So the idea is this. Say you had two objects right here, okay, and a cart. You're going to push that cart on the Earth and on the Moon. So you're just pushing that cart and you're trying to accelerate, all right? So you draw an FBD of both objects, all right? So you have normal, gravity, push. Let's ignore friction for now, all right? This guy, you also have normal, gravity, push, all right? So this would be the FBD of both objects, normal, gravity, push, right? Notice that this guy's gravity arrow is going to be smaller than that guy's gravity arrow, right? The weight is less. Why is the gravity less? Not because the mass is any different, but because the second number that you multiply mass by to get gravity is different. So that guy's gravity arrow is going to be smaller, all right? However, the mass is the same. Now, what is the significance of that, okay? This guy will be just as difficult to accelerate horizontally. Why? Because the mass is the same. And remember, mass determines how difficult it is to accelerate horizontally. So once again, if I take this guy, if I move it side to side, all right, it'll feel exactly the same on the Earth as on the Moon, all right? Gravity is literally just the size of that gravity arrow. So that only affects things vertically. So if I try to lift this thing to counteract gravity, the weight, okay, on the Earth, this will definitely lift heavier than on the Moon. This will be easier to lift on the Moon. But if I try to move it side to side in any other direction besides vertical, it'll feel exactly the same, right? Because mass is a more universal thing. No matter which direction I try to move it, it'll be hard to accelerate. Gravity is literally just this downward arrow, and that only affects vertical things. So vertically, yes, moving it vertically, it's easier on the Earth compared to the Moon, right? But every other direction, right, they'll feel exactly the same because their mass is the same, all right? So mass is a universal idea about how difficult it is to accelerate in every direction, right? Gravity is literally just a vertical thing, a vertical arrow that only affects things vertically, okay? All right, so let's just practice this a little bit. Why don't we try this, these two questions, all right? First question, if you know the object's mass, you should be able to find the force of gravity, okay? Likewise, if you know the object's weight, you should be able to find its mass. Why don't you guys try these two problems, all right? And you can check your answers with, I don't know, I'll have some answers on my subnotes. And then once you guys calculate these, you can check your answers with your subnotes, okay? And then I think that's all with today's lesson. All right, so just do these, check your answers, and if you get them both right, you're good to go. And I will talk to you in a later video.